So now, I just did a step-by-step build of this circuit. I explained things in a lot of detail. Most of the stuff though, you should also measure with the multimeter if it is new to you. So we are going to take these probes here instead of pushing them on components, and I'm trying to aim through the camera instead of in person, so it doesn't really line up exactly where it looks on camera. But in any case, there we go. We got our black probe to the negative supply. We can turn the multimeter on before we do this. Set it to V, measure voltage. Measuring voltage is very safe, especially if you have a multimeter that has auto ranging right there. And even if it's not auto ranging, it has numbers, it's pretty safe to leave it on measuring voltage all the time. So as long as you don't exceed the voltage of the meter, which I believe this one can go up to 600 volts. So AC or DC. So we will attach that one to that one. So one thing that does is allow me to not have to block our view holding the probe right there, and also this is more steady right there, especially with this cheap board. Shuffling components a little bit can change the resistance of the connections and therefore give you a different voltage reading even. So there we go. This is meant to be about 2.5 volts and it's close. So again, circuits are I'll say like 2.5 volts when I'm making the video, but it's probably slightly different. That's okay. This is not precision circuit. Even the supply rail right there, we're losing a little bit of voltage along the way. And I was making a different video, different topic. I was wondering if the supply voltage at the rail would change if I remove the LED, and I'm going to try to hold things steady right there if we didn't have current going through the load. And I think it did. May have changed a little bit, not really much, but yeah, let's go back down a little bit. So the extra current that we have to draw from this will kind of lower the voltage at this supply rail. We could probably fix that with the capacitor. Again, something we could do in another video. See if the rail voltage stays a lot more steady with the capacitor on there, which, you know, it should. But in any case, that's what capacitors are commonly used for, to steady a voltage in a spot, especially when there's changes going on in the circuit. So we looked at the reference voltage. It's half of that supply voltage. Let's get back to what I was working on. So this is just kind of a spur of the moment video. I didn't really plan this out too well. So we have about half the supply voltage. Our signal voltage over here, trim pot. So again, this was one reason why I removed the LED. I noticed that our reference voltage changed when technically it shouldn't, you know. And so looks like it went a little bit higher there and a little bit lower there, which I kind of expected the opposite. But in any case, you can see, turn the trim pot up high enough, we get a high output. And I'll kind of dim the lamp there so it shows up a little bit better. And then lower the trim pot below about halfway right there. We get a low output right there. So reference voltage basically stays the same. Now, there is that slight shift again. You overcome that with hysteresis, where you get a more well-known shift, so that you actually use the output to change the reference voltage just a little bit in the direction that helps lock the output in place right there. So it's easy to overcome it, but you won't have like a middle ground region where you keep bouncing above and below that reference voltage, because the reference voltage moves a little bit. It's called a Schmidt trigger and hysteresis. So that is our signal voltage right there. Again, somewhere around 2.5 volts is where we will get the change. So there you can see. Now I'll go down, and multimeter, especially the auto ranging meters, are not, you know, accurate. It takes a little bit to get, when the voltage is changing, to get to the actual voltage. So when it is changing, it is not accurate at all. Something to be aware of. Oscilloscopes are better for that. So in any case, above 2.5 approximately, red LED, and I don't know why it's not showing up so good. And then below, blue LED. So now I adjusted the light sensitivity of the camera, and let's get that red LED lit up. I think that might be a little bit better. But in any case, there we go. So that is looking at the voltages of the inputs. We got our reference voltage, which is fixed. Generally, that's what the reference voltage means, the one that's fixed. And then our signal voltage, the one that is changing for the most part. And, you know, there's some variations on it, but that's the main premise. Now, another thing I want to look at is the output of the LM358 that I'm using right here. And maybe there's manufacturers that sell better ones or something. But in any case, we basically want 5 volts at the output right now because the output is high. But this is what's called a single supply op amp. It's made for, you know, ground being 0 volts, the negative supply right there, not a middle ground point between the positive and negative. That'd be a split supply. The negative supply is ground, 0 volts. And then we got a positive voltage in relationship to that, 5 volts in this case, as we measured with the meter before. And so when you have single supply components, integrated circuits, then typically they don't get the full 5 volt supply in this case anyways, whatever the positive supply is. So we will pluck the LED and see, even without a load right there, it falls a bit short, you know, somewhere around about 1.5 volts. And then with the load, maybe it'll fall like 2 volts from that supply voltage. And stuck the LED in the wrong spot. That's why it wasn't lit up. A good reason why LEDs won't be lit up when they should be. Also, if you put them in backwards, something to be aware of. So yeah, there you can see we fell short of the 5 volts. That was that first test. Now we're gonna go, when it comes to the output, we're gonna go to ground. And I say this all the time, single supply op amps get ground really well, some better than others. Apparently this one not so good with a load. That's the main thing right there, with the load. We got less current going through the blue LED, even though it's pretty bright right there. We don't have to take current measurements. We can get a pretty good idea with the power supply. About 2 milliamps of current right there. I should have kept holding on to the screwdriver. And then we turn the trim pod up to a high output right there. And there you can see about 6 milliamps of current. And so we got less current than we expect with the resistor we have, because again, we're not getting as much supply voltage as we want. In fact, we can see that right now. So that is 0 volts there. We only got about a 3.3 volt difference across that load. So these op amps aren't great at providing power. I mean, we just need the LEDs lit up, so that's all the power we need. But it's not doing a great job. So there we go. And now you're going to see when I remove the blue LED, we actually have a connection to ground. I don't know where this negative voltage is coming from. So, but it's 0 volts. There's no voltage at all. And again, if I put the LED in though, so that's what we want. We want 0 volts, a ground connection. But when we add the LED, the transistors within the integrated circuit are not conducting well enough to keep the voltage all the way to ground right there. So we got that right there. So you can learn about the building of integrated circuits and stuff. And other manufacturers might have a better transistor setup where you have a better connection. These were cheap, so maybe they don't do as good as more expensive ones. Something to be aware of when you are, you know, designing your own circuits and stuff. But yeah, you want to usually just use the integrated circuit to send a signal to transistors. We could easily use MOSFETs in a push-pull configuration where they'll make a much better connection, in this case to ground while the load is being powered, and in this case to the positive supply when the load is being powered. Those MOSFETs though would be inverted. So when this has a high output going to the MOSFETs will have a low output. But you could just send that output to another set of MOSFETs, and so it'll bring it back to the final output being the same as what we have at the output at the comparator here, right there. It's an op amp wired as a comparator. So, any case, that was the main point of this video, just to get a better idea what the actual output is right there. And again, not that great even without a load when it's a high output, but that's to be expected with single supply op amps. Something to always be aware of. And unfortunately, I thought this was kind of like a 555 where you still get a really good ground connection. You know, not perfect, but pretty good with a low output, even with the load, but we don't have that. We're about a volt off, so not as good as I thought. But again, this is kind of stuff you want to prototype before you build a serious circuit, because it's easy to forget. When you look at the schematic kind of assumes everything is perfect right there. So we're either going to be high or low. That's all you really know. So you may think you got a full 5 volts when you actually don't. You may think you got a full negative output right there when you don't. And in reality, for these LEDs, doesn't really matter. We just want them to light up enough to see them, so we're doing fine. But we do have voltage loss when it comes to the output that you got to be aware of, and it may be a reason why circuits aren't working like you think they should. So you have to be aware of what the output's doing. In any case, rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.